In this video, we're going to look at a theory called the valence bond theory. And essentially, this describes how a covalent bond forms through the overlap of atomic orbitals. In order for a valence bond or a covalent bond to be created, there are two conditions that must be met. First, an orbital on one atom must overlap with an orbital of another atom. And it turns out that the single electrons in each of these respective orbitals combine to create an electron pair. A couple of additional pieces of information are that the amount of overlap does dictate the strength of the bond in question, and there are multiple types of overlap that we'll discuss here in just a few minutes. Depending on the atoms that are involved in this overlap, you can have relative strengths, which are measured in values of energy or kilojoules per mole, and you can have respective lengths also to the bond. So if you compare the three bonds of carbon-carbon single bond, carbon-carbon double bond, to carbon-carbon triple bond, you can tell that as you increase in the number of bonding pairs, the amount of energy also increases in those respective bonds. So therefore, this triple bond is stronger than the single bond between carbon and carbon. The length also, as the bond gets stronger, does shorten as well. And so if you look down the bond length, 150.6 picometers or angstroms for a single carbon-carbon single bond to 120.8 picometers for a carbon-carbon triple bond. So triple bonds are shorter than single bonds. These particular values you can find in bond energy charts that are available in your textbook. So let's look at the two main types of bond or atomic orbital overlaps. The first kind of overlap is an overlap that we call a sigma bond. And a sigma bond, you can write out the word or you can use the little Greek symbol that I have written here. And a sigma bond can happen in one of three ways. It can occur where you have a s orbital and an s orbital, so one s orbital from one atom, one s orbital from another atom, and what will happen is these two will overlap with one another. And the overlap space is the space where you have this attraction that helps then create that covalent bond between the two atoms. You could also have an s orbital from one atom and one single p orbital from another. And how that overlap would look is you would move the p over and you would have a space of overlap between the two, and that is where your covalent bond would be. And then you could also have a p orbital and a p orbital from two different atoms overlap. And they overlap end on end. So you would move the p orbitals over and they would overlap in the center area right here. And that would be what you would consider a sigma bond. The second kind of overlap that you can see is called a pi bond. And a pi bond, you can write it out or you can use the symbol, the pi symbol that I have written here. And the way that a pi bond works is it's no longer an end-to-end p orbital overlap. Instead, you have two p orbitals that are parallel to one another, and they actually overlap each other kind of on the side of the p orbitals, rather than an end on end like you would see here. So this is what would be created as a pi bond, where you have p orbitals and p orbitals overlapping non-end to end. So what is it that's important? Why do we want to call them sigma versus pi? Well, it turns out that the first time an atomic orbital overlaps between two atoms, that is always going to create what we call a sigma bond. Any other orbital overlap that is done between two atoms then creates what we call the pi bond. And the pi bond is going to be the second of a double bond or the second and third of a triple bonding pair within a triple bond. And so what I would like for us to do in these particular examples, I gave 4 examples, is let's determine the number of sigma and pi bonds in the following molecules. So we're going to go through and we're going to highlight every sigma bond in our molecule 1, and that is the very first, or only if there's a single bond, that's the bonding pair that's considered a sigma bond. So here's a sigma bond, sigma, 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 sigma. These are all the bonding pairs in this particular molecule are called sigma bonds. So the number of sigma bonds here are 1, 2, 3, 4, 5, 6, 7, 8. How many pi bonds? 0. So now let's go over to the second molecule and let's look. This is a sigma, 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 sigma. All of those that I've highlighted are sigma bonds, but a pi bond would be the second if there were 2 bonding pairs between 2 atoms. And so to count the number of sigma bonds versus pi bonds, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 sigma bonds, and it turns out there are 2 pi bonds. So now let's go to the third molecule. This molecule, we're going to highlight at least 1 bonding pair between each atom. So we're going to go and use our same colors for sigma. Green, green, green. So that's 3 sigma bonds. And whenever you have 2 additional bonding pairs above the sigma, each one of those, 1, 2, are considered pi bonds. So these will also have 2 pi bonds. Now let's do our last substance, our last compound, which is benzene. And we're going to highlight all the sigma bonds, so at least 1 bonding pair between each atom, like such. And then we'll highlight all the pi bonds, 1, 2, 3, and we'll count total. So we know that there are 3 pi bonds, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sigma bonds. And so that's how you determine, out of a covalent bond, what we call each of the bonding pairs. The first bonding pair is considered a sigma bond, and the orientation of that overlapping of the atomic orbitals occurs in a specific of those 3 ways. And any additional bonding pair, the second in a double bond or the second and third in a triple bond, are all called pi bonds, and they occur by overlapping not end-to-end p orbitals, but to the side. So this is atomic orbitals.